Okay, lesson 3. So we just finished talking about Boyle's law. Now we're going to move on and look at a couple of more laws that are very useful. So gases and temperature changes. First, of course, we want to go back and remember that temperature and kinetic energy are directly related. So as temperature increases, the amount of kinetic energy increases. And we also have that direct relationship between temperature and volume and pressure. And direct relationship means that one will affect the other. So basically, if a gas, for example, is at 0 degrees and it's heated to 273 degrees, its volume will actually double. Now, this is a standard amount. The fact that this 273 degrees causes the volume to double, okay, so an increase from 0 to 273 degrees causes the volume to double, brings us to the Kelvin scale and absolute zero. So gas expand with increasing temperature. So that's what happens. You have the temperature causes gases to spread out and expand. So this guy, Charles, realized that regardless of the gas, it didn't even matter at all. The gas particles actually stop moving at negative 273 degrees Celsius. So basically, the conclusion is that at negative 273 degrees Celsius, the volume of the gas is 0. So this is when the particles stop moving. And Lord Kelvin used this to develop, of course, the Kelvin scale. So what the end result of that, of course, is that if you're looking for the temperature in Kelvin, you take your degrees Celsius and you add 273. You can do the 0.15 or not. It doesn't really matter. But Kelvin is degrees Celsius plus 273. So the starting point of the Kelvin scale is absolute zero, or 0 Kelvin, or negative 273 degrees. So that's when gas particles do not move. So the kinetic energy of the gas is 0 and the volume is 0. Now that brings us to Charles's law. The volume of a fixed mass of gas is proportional to its Kelvin temperature. And so in order to use Charles' law, you must have a constant pressure. So pressure must be constant for this to occur. And what you get, you have your initial volume and your initial temperature is directly related. It is proportional to your final volume and your final temperature. So if you go back and if we look at this type of diagram again, remember, temperature is staying the same, pressure is staying the same, so pressure is not changing, okay, so constant pressure. But if we add heat, if we increase the temperature, the volume will increase, okay, so these are directly proportional. If one decreases, if volume decreases, temperature will decrease. If temperature increases, volume will increase as well. So that is Charles' law. So if we look at calculating using Charles' law, basically, for example, you may get questions like this one. Using a glass syringe, a scientist draws exactly 25.5 centimeters cubed of oxygen. So this would be your volume, okay? And at 20 degrees Celsius, so that's your temperature, of course. After heating the syringe in an oven at 65 degrees, so we're assuming this is our final temperature, our second temperature for 30 minutes, what volume will the oxygen occupy if the atmospheric pressure stays the same? This is important to recognize. You cannot use Charles' law if you do not have a constant pressure. So we have the initial volume, the initial temperature, and the final temperature. So what we're looking for is that final volume. So once you do the calculations, this is what we're given. Okay, the initial volume, the initial temperature. This is where it was 20 degrees, but you have to convert that to Kelvin. And then the final temperature of 65, once it's converted to Kelvin, and then you substitute that into the equation. So that's probably the trickiest part, is remembering to make sure when using Charles' law that you need constant pressure. And you must use the Kelvin, not degrees Celsius. So we take these numbers, 25.5 cubic centimeters, 293 Kelvin, 338 Kelvin, plug them into the equation, rearranging, of course, and remember, this is what a lot of students have trouble with, is rearranging equations, and now the triangle is not going to work because you have more than one variable, so you have to solve for volume 2. The equation is T1 V1, or sorry, get rid of that. V1 over T1 equals V2 over T2. So if we're solving for V2, okay, we're going to have volume 1 times temperature 2 divided by temperature 1. So when you do that, you should get a volume of 29.4 cubic centimeters. So another example, you may want to pause right here and try this one to see if you can get the right answer. So you have 2.5 liters, so that's your volume, dry helium. Your initial temperature is 23.5 degrees Celsius. Don't forget to convert that to Kelvin. The balloon is placed in the freezer overnight and its volume is found to be 2.15 liters. If the pressure is constant, that's key, then what is the temperature of the freezer? So we're looking now for the final temperature. So given a volume in liters, we're given the temperature in degrees Celsius. We need to convert that to Kelvin. And then we have the final volume. So we're looking for that final temperature. Now, when you do find the final temperature, you are going to find it in Kelvin, of course, and you may want to convert that back to degrees Celsius. And the temperature of the freezer is 18 degrees Celsius. Okay, so that brings us then to Guy-Lussac's law. And this one deals with the pressure of a fixed amount of gas at constant volume, and that's directly proportionate to its Kelvin temperature. So with Charles' law, you have constant pressure and you have volume and temperature directly related. Guy-Lussac's law, you have constant volume and your pressure and your temperature is directly related. So same type of situation. You have a cylinder of chlorine gas stored in a concrete lined room that can withstand 50 atms of pressure. The pressure is 35 atm at 23.2 degrees. Accidental fire next door causes storage room to heat to this degrees. What is the pressure reading at this temperature? So the pressure is 35. Okay. So what is the final pressure once the temperature goes up? So same thing, we're always dealing with Kelvin. The initial pressure is 35 degrees, 35 atm. The initial temperature is 23.2 degrees Celsius plus your 273, which gives you 29.62 Kelvin. Your final temperature, which was 87.5 degrees Celsius, which is 360.5 Kelvin. Plug that into the equation, do your calculations, and you end up with a final pressure of 42.6 atm. So the pressure of the storage room is 42.6, and I think it could withstand 50, so that's fine. So to summarize, so far what we've done are 3 laws. We have Boyle's law, we have Charles' law, and we have Gay-Lussac's law. Okay. Basically, pressure and volume, you get a constant. You get your volume over temperature, you get a constant. You get your pressure over temperature, you get a constant. So now we can actually combine all of them nice and neat into this little useful formula, and we will talk about that